Okay, so we're going to go through lesson 7 through 10 tonight. So we're going to start with lesson 7, which is common distributions. So remember talking about the normal distribution. It's that bell-shaped distribution that has a mean of 0 with a standard deviation of 1. It's also known as the z-distribution, so that's what you plug your z-scores into to get your p-values. And 100% of these observations fall under the curve. So if your sampling distribution is approximately normal, we construct a normal distribution with a mean equal to the hypothesized parameter, which is the number in the null hypothesis, and the standard deviation equals the standard error, and then you can find your p-value. So remember, the central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed. So as your sample size increases, the more normal or bell-shaped your distribution becomes. And then just remember that a z-score or a standardized score is the distance between an individual score and the mean and standard deviation units. So using the normal distribution, we can conduct hypothesis tests and construct confidence intervals. So to conduct a hypothesis test, we use 5 different steps, and these steps will be reiterated throughout this presentation because just for hypothesis testing, they're very similar just as they are for confidence intervals. But first, you're going to check your assumptions, which is typically just making sure that the variables work for this type of test you're using, and then or checking that the sample size is sufficiently large. And then if it meets the assumptions, you can write your hypotheses, and then you can calculate the test statistic, and then based on the test statistic, you can determine your p-value, and then based on the p-value, you decide whether to reject or fail to reject the null hypothesis, and then you state a real-world conclusion, which just puts everything back in the context of the original problem. So first off, the standard normal distribution method, when you're using it, the test statistic is standardized for the z-distribution. So to calculate a z-score, the formula is x minus x bar over standard deviation. And then when you're conducting a hypothesis test, the sampling distribution is centered on the null parameter. So that's the number in the null hypothesis. And then the standard deviation is just known as the standard error. And then the formula for the test statistic is below. So for an example, the proportion of female students, so are more than 50% of all World Campus Stat 200 students female. Data were collected from a representative sample of 501 World Campus Stat 200 students. In that sample, 284 students were female and 217 were male. So we're going to conduct a hypothesis test based on this information. So I laid out all the steps here. We're just going to walk through each step, and then after that, we kind of go through the other hypothesis testing procedures more quickly just because it's such a reiteration of the 5 steps. So we're just going to go over, basically just go over this problem. So first, we're checking our assumptions and writing our hypotheses. So here we already know that our data is of a sufficient sample size, so we can go ahead and write our hypotheses, which is our null hypothesis is p equals 0.5. Because we want to see if more than half of the students are female or male, and then, or we want to see if more than half the students are female. So that's what our alternative hypothesis is: p is greater than 0.50. So now we have our hypotheses, we can calculate our test statistic. So to calculate our test statistic here, we need our p-hat, our hypothesized parameter, and our standard error. The standard error wasn't given in the original problem, but this is, I'm recording it. I'll post it on YouTube if you want after. So, but yeah, so our hypothesized parameter is 0.50, and the standard error that comes from a randomization distribution is 0.022. And then we can plug that into the test statistic to get 3.045 as our test statistic. So then we can use the z-distribution to find our p-value here. And once we plug in the test statistic to the normal distribution, we get a p-value of 0.0011. And then that is obviously sufficiently, a sufficient p-value. It shows that our data is sufficient. It is less than the alpha level, which is 0.05, so we can reject the null hypothesis. And then the last step, don't forget to put it in to state your real world conclusion, and you can say that there is evidence that the proportion of all World Campus Stat 200 students who are female is greater than 0.50. Okay, so we just did hypothesis testing. Now we're going to go on to confidence intervals with normal distributions. So you know that the general form of a confidence interval is your sample statistic plus or minus your multiplier times the standard error. So for here, we're using a z-star as our multiplier with the normal distribution. So something to remember here is that your mean is equal to your sample statistic, and then your standard deviation is equal to the standard error. So the z multiplier can be found in the z distribution. And if you were to put it, for example, in terms of the 95% rule, for example, your z-star would be 2, since 95% of the observations on a normal distribution fall within 2 standard deviations of the mean. So that's just the general form of a confidence interval for and then we're going to move to binomial probabilities now. So remember that binomial random variables, this is kind of a shift from what we were just doing, but binomial random variables are a specific type of discrete random variable that counts how often a particular event occurs in a fixed number of tries or trials. So for a variable to be binomial, all of the following conditions have to be met. So it makes it a little bit easier that there's clear conditions. If it doesn't follow one, then that means it's not a binomial random variable. It has to follow all 3 of them. So there must be a fixed number of trials or a fixed sample size. The probability of success must be the same on each trial, and the trials are independent of one another. So an example I like to use of this is the number of tails you get when flipping a coin 10 times. So if we go through the checklist for this one, yes, there are a number of fixed trials. The sample size is 10, it's fixed. 2, the probability of success is the same on each trial because when you're flipping a coin, the probability that you're going to get heads or tails is always 50%. And then the trials are independent on one another, so whether you flip heads on the second trial does not affect whether or not you will get heads or tails in the third trial. So you can find the mean and standard deviation of binomial probabilities through these formulas. So the mean of a binomial random variable is just n times p, which is the sample size, times the probability. And the standard deviation of a binomial random variable is the formula listed below, which I won't say because it's a mouthful, but you can see these formulas here, and there will be a review question coming up on one of these formulas, so just make sure that you note those down. Okay, so for our first review, for the SAT math scores, this is the data that we're given. Let's apply the empirical rule to determine the SAT math scores that separate the middle 95% of scores. So this is a shorter question, so I'm going to give you about a minute to go over it. Okay, so the answer here is B. So what we're going to do to get this is to find the middle 95%, we're given 500 as our mean. And then since we're using the 95% of scores, our multiplier here would be 2. And then we multiply the multiplier by the standard error, which is 100. So once we add all that out, or multiply that out, it comes to 500 plus or minus 200. And then that comes out to 300 and 700. So if you guys have any questions on any of the review questions, you can ask me at the end, definitely. So here's a second review. Which of the following is not an example of a binomial random variable? So this is one of the shorter ones. Okay, so here we're just going to go through the following answers. So remember the checklist that we have when conducting a binomial random variable. So all of the following conditions must be met here. So the number of correct guesses at 15 true or false questions when you randomly guess all answers. So if you're randomly guessing a true-false question, the probability is similar to that of flipping a coin 15 times. So A and D are kind of similar. So it's about 50-50 since there are two options that could be met. So that's why A and D are examples of binomial random variables. And then C, the number of left-handers in a randomly selected sample. There's a fixed number of trials here. They're independent of one another, and the probability of success is the same on each trial since they are random. And then the reason why B is the answer here is because the number of winning lottery tickets, so there is a fixed number of trials, which is 20, but the probability of success is not the same on each trial since each lottery ticket is different. But if each lottery ticket was the same, then that would make it a binomial random variable. Okay, so here's the last review question for lesson 7. In a very large class, each student flips a fair coin 10 times. The number of tails that each student observes is recorded. Compute the expected mean of that distribution. Okay, yes. So the answer here is 5. So remember the mean the mean for a binomial random variable is n times p. So here we multiply n times 0.5. We get 5 as our answer. So good job. Okay, so next we're moving on to lesson 8, which is inference for one sample. So we're going to start with one sample proportion and then move into one sample mean. By the time we're end with this, it's going to sound a little repetitive, especially with the hypothesis testing. But I have a chart for each formula that kind of connects them all together, which I think makes it a little bit easier at the end of each section. So first with one sample proportion. So each assumption is different for each type of test that we do. So here, the assumptions are that when we multiply everything out, it's at least 10, and then that means the sample distribution will be approximately normal. So if the assumptions are met, then we can use the normal approximation method. But if the assumptions are not met, then we use binomial distribution method, which you have to use like Minitab to use that. So with confidence intervals here, we have to make sure that there's at least 10 successes and 10 failures. Again, those are our assumptions. And then if it passes that test, we can use the normal approximation method to solve for our confidence interval, which the formula is there in the little pink box. I'm not going to bother reading it because it's a mouthful, but there you go. So that's really, if we have at least 10 successes and 10 failures in each group, we can then go on to say, okay, we can use this confidence interval. It's really just testing to make sure that our sample size is sufficiently large enough. So just remember that the value of the z multiplier depends on the level of confidence. So whether or not you have a 90% confidence interval or a 95% confidence interval, you know that for 95% confidence intervals, you use 2 as your z multiplier. That's just an example. And then the standard error is computed using p-hat as an estimate of p. You just know that since we use our statistics to give us an estimate of what our parameter is. So sometimes you're given a margin of error and a level of confidence and have to determine the minimum sample size to get those areas, which I think is more of a working backwards. So you can find your sample size using this formula to estimate your population proportion. It's really important to remember that when you do this, whatever answer you get, if you get a decimal, you have to round up. You have to round up to a whole number, because you want to make sure that that sample size can give you those level of margin of error.
Hello.
Okay, so if you don't want to know the estimated value if you don't know the estimated value of the proportion sometimes, which is given by the p with a little squiggly line over it, if you're not given that, you can use 0.50 because it will provide the largest sample size calculation. So if you think about it, that's the widest proportion you can have there. So it will give you the minimum sample size, even if your actual estimated value of the proportion is less than that. Okay, so moving on to hypothesis testing for one sample proportion. A hypothesis test is used here when you have one categorical variable, and then the hypothesized value is symbolized by P of O because it's the value in the null hypothesis, so that's pretty easy to remember there. And then the assumptions here again are just that when you multiply these factors out, they have to be at least 10, which is just really saying that there is at least 10 successes and 10 failures. And then when you meet those assumptions, you can create your sampling distribution. So again, here's that 5-step process that we're going to go over. You want to check your assumptions and write your hypotheses. Your assumptions is that you have at least 10 successes and 10 failures, that your sample size is sufficiently large there. And then once you meet those assumptions, you can calculate your test statistic, which the formula is there on the pink box on the right. And then once you calculate that, you can plug it into a normal distribution to find your p-value. And then you can make a decision based on your p-value, whether to reject or fail to reject the null hypothesis. And then you can state a real world conclusion at the end. Okay, so moving on to one sample mean here. You remember the central limit theorem I just talked about at the beginning of the presentation. It's just stating that as your sample size increases, the more normal it will be. And here in this case, for one sample mean, a large sample size is defined as one where your sample size is greater than or equal to 30. So here with one sample mean, we use the t distribution instead of the z distribution. And the only difference between the t distribution and the z distribution is that the t, the height of it varies based on the sample size. So you guys remember that's where degrees of freedom plays a role. Every time you know that degrees of freedom is different based on your sample size. So that's really the only the difference between the t distribution and the z distribution. So we're going to be using that when we conduct our confidence intervals and hypothesis tests with one mean. Okay, so first with confidence intervals, we know that this is the general form of a confidence interval, and then we have the confidence interval for a population mean, so you can kind of see the similarities. The difference here is that we use the t-star multiplier, and then we have a standard error equal to that of a population mean, which is just the standard deviation divided by the square root of n. So you know some of those standard error calculations can be a lot, but this one is not as bad as the other ones are. Not that the other ones are necessarily bad, but they just take a lot more work and time to find it. So again, you can compute a necessary sample size, just as we did before with one sample proportion. And you're given, again, I'll reiterate that you're given a certain level of confidence and a margin of error. But this is only different since because the t-distribution is different for each degree of freedom. Just remember that. And then once you get your sample size, you round your answer up to make sure that you can meet that minimum level to get the margin of error confidence level that you want. So again, with hypothesis testing here, you're going to check your assumptions and write your hypotheses. So here with one sample mean, in order to use the t-distribution, the sampling distribution must be approximately large, which in this case, your n is greater than or equal to 30. And then once you meet your assumptions and write your hypotheses, you can calculate your test statistic. And then you can use the t-distribution to find your p-value, and then decide whether to reject or fail to reject the null hypothesis based on the level of alpha that you use compared to your p-value, and then state that real-world false conclusion. Okay, so this is the last section in lesson 8 that we're going to go over. So paired data is dependent samples. It can either involve taking 2 measurements on the same subjects or taking 1 measurement on each of 2 related subjects. So the first way, you can weigh 1 participant both before and after something, such as the effectiveness of a diet plan. So you can weigh them before and after the diet plan, and then compare the data, see how much was lost to see if it was effective. And then the second way, you can study pairs that are related. So twins, husbands and wives, sisters and brothers, something along those lines, as long as they're related subjects. And then when you're constructing your confidence intervals or your hypothesis test, you use the difference here. So it's the procedures are pretty much the same. You just want to use as your sample the difference between the two. So this looks familiar to the confidence interval for one sample mean, but really the only difference is that you use the difference between the two means, and that's what your X bar is here. Okay, so hypothesis testing, there's quite a lot of formulas for paired means here, because the main test statistic formula kind of goes into finding the standard deviation and then the observed sample mean difference. So it can get kind of deep here. But first, the same thing, you're going to check your assumptions, then write your hypotheses. You have to make sure that your data is paired and dependent, and then just make sure that the sample size is at least 30. And then after that, you're going to calculate your test statistic. I have the formulas on the right. I'll show you a slide. I think it's one of the next slides that kind of helps put all the formulas together. So don't worry really about those at this moment. So, and then once you get your test statistic, you determine the p-value from the t-distribution, and make sure you've used that degrees of freedom. And then from there, you're going to make your decision and then state a real-world conclusion again. So here's just everything that I just said basically for lesson 8 summed up in one slide. So we talked about confidence intervals and hypothesis testing for one sample proportion, one sample mean, and paired means. So you can kind of see the similarities between the assumptions and the formulas that you use, such as standard error here. But it all can kind of seem like a lot sometimes, so I just wanted to put it all together so you can see the patterns between all the formulas. Okay, so this is the first review for this round. So this question, I'll give you about 30 seconds to answer, and then we're going to go over it. So you can type your answer in the chat box once you get it. Okay, yes, good. The answer is D. So, Here, to calculate the degrees of freedom, just remember that you take n and subtract 1. So here our n is 66,831. So we're just going to subtract 1 from that, and our answer is D. So good job. So for the next review, I'm just looking for you guys to calculate the test statistic. I put the formula at the top just for your convenience so you can reference it while you do it. But go ahead, take like a couple moments to do that, and then we're going to go over it together. Okay, good job, you guys. So 3.77 is our answer here. So I just kind of laid out the data that we're given and that we use to find the test statistic here. So you take your x bar, subtract it from the null mean, and then divide that by the standard deviation divided by the square root of n. So you guys definitely did a good job with that one. So next we're moving on to lesson 9, which is inference for 2 samples. So it's kind of similar to what we just did, except it's 2. So we're using 2 proportions and 2 means here. So first with 2 proportions, we're going to start. So the assumptions here are similar to that of 1 proportion, except you just want to make sure that they're the same for both groups. You want to make sure that the assumptions are met for both groups and not just one or the other. And then you can go ahead and assume that you can use that they are approximately normal and use the normal approximation test here. So first with confidence intervals, if the assumptions are met, you can approximate it using the normal distribution with a mean of p hat 1 minus p hat 2, and then that standard error, which I won't go ahead and read because it's a lot of variables there, but and then that's your standard error formula, and then you put those together. It's just the same basic format for a confidence interval, which is your statistic plus or minus the multiplier times the standard error. And then with hypothesis testing, we're going to be using the same 5-step procedure. You want to make sure that there's at least 10 successes and 10 failures in each group, like we've been doing so far. So first, remember to check your assumptions and write your hypotheses. Our assumptions here are that there are 10 failures and 10 successes in each group, and then, or at least 10 failures and 10 successes. And then the 2 groups must be independent, so they can't be dependent or related to each other. And then you calculate your test statistics. So when you're computing the standard error for the difference, you want to make sure that you use a pooled proportion instead of the difference between the two. So the formula for the pooled proportion is just right here. This is what you want to use. Sometimes people can get confused and just use the difference between the two, but you want to make sure that you use the pooled proportion because that can lead you in the wrong direction. And then once you get that, you can use the pooled proportion to calculate the standard error. And then once you get the standard error, you can calculate your test statistic. So once you get the test statistic, of course, you determine the p-value, and then you decide between the 2 hypotheses and then make a real-world conclusion. So that was independent proportions. Now we're going to go into 2 independent means. So first with confidence intervals, again, our assumptions here are a little different from the proportions. So you want to make sure that each sample size is at least 30. But so far you can see a running pattern with the means and the proportions here. But your confidence interval then for the 2 independent means can be the difference plus or minus t star times your standard error. And then here with the t-distribution, you want to make sure that you use the correct degrees of freedom. So the degrees of freedom we use here is just the smallest n minus 1. Okay. And then we're going to be using the same 5-step process here for the hypothesis test. So you're going to check your assumptions, make sure that the populations are greater than or equal to 30, and then make sure that the 2 groups being compared are independent of one another. And then you're going to calculate an appropriate test statistic, which is just the difference over the standard error. And then determine the p-value, of course, using the t-distribution, and then decide between the null and alternative, whether to fail or to fail to reject, or whether to reject or fail to reject the null hypothesis, and then state a real-world conclusion. So here's exactly what I just talked about. Same as last time in this form, it kind of puts everything together. So we discussed the 2 independent proportions and the 2 independent means and their respective confidence intervals and hypothesis tests that go on. You can see the assumptions are here with 30 and at least 10 successes and 10 failures. And then the confidence intervals for each and the test, how to calculate the test statistic. So I think we have a review here. Yep. So we use the data in the table to test if there's a significant difference in the proportions who choose to split between younger and older players. Just here, we're going to just choose the hypotheses that are designated here. Okay, great. B is our answer here. So we're just looking here at the difference in proportions. So we're using the two groups here. So you want to make sure that you don't use 0.50 as just maybe if you got confused between the split and steal options, but we're looking at the difference in proportions here, so that's why it's P1 over is equal to P2, and the alternative is P1 is not equal to P2. So good job there. And the next question is just using the same data from the previous question, calculate the sample proportion for a group over 40 that steal. So here we're just calculating our p-hat. Yesterday, some people got confused that you had to use formulas, like crazy formulas, but it's just a pretty simple formula to calculate the statistic here. Okay, yes, so D is our answer here. So remember just to calculate the sample proportion, you just want to take the number in a category over the total number in that category that you're looking at. So in this case, we're looking at the group over 40. So we take 76 because those are who steal, and then we take that over the total in the group, which is 192, and we get 0.396. So great job, guys. So our last review for this unit is just to compute a 90% confidence interval for the difference in mean commute time between Atlanta and St. Louis. So I provided you with the T-star here, and then everything else is given to you. So go ahead. Okay, we're going to go over the answer here. So we're going to go through the X bar one that we're given is the mean of group 1, which is 29.11. And then we subtract 21.97, which is the other mean. And then just add and subtract the t star multiplier, multiply that by the standard error, which is which we take the standard deviations and square them and then divide each by n, which both of their n's just happen to be 500. And then we get a margin of error of 1.85, and then we get our final answer of 5.29 to 8.99. So overall, pretty good job, you guys. We're going into our last unit here, which is lesson 10, which was one-way ANOVA, which you guys have most recently done. So you learned about the F distribution here. We've talked about Z, T, and now we're adding F distribution. For the F distribution, we can compute F statistics, which we can use to determine p-value for a one-way ANOVA. And if you've noticed, there's 2 degrees of freedom we use for the F distribution. So there's between groups and within groups. The between groups is sometimes referred to on like Midterm or Stacky as the numerator degrees of freedom, and that can be calculated by k minus 1. K is just the number of groups, and then you subtract that by 1. And then within groups is our denominator degrees of freedom, and it's calculated by n, which is your sample size, minus k, the number of groups. So with our hypothesis tests, everything is pretty similar as to what's been going on, except there's some different assumptions for one-way ANOVA. The samples are independent. The response variable must be approximately normally distributed, or the sample sizes have to be greater than or equal to 30. And then the population variances have to be equal across the responses. So that's basically just saying that the largest sample standard deviation divided by the smallest sample standard deviation can't be greater than 2. And then once those assumptions are met, we can calculate we can write our hypotheses. And our hypotheses are just say that our means, for example, our group means are equal to each other. Each group mean is equal to each other for our null, and then for our alternative, not all of them are equal. So you can see some patterns as to what we've been using before. It's pretty much similar. So after that, you're going to calculate your test statistic. You've seen all that information that you're given through Minitab, and it gives you the different degrees of freedom and your F statistic that you can look up on the F distribution as long as your degrees of freedom are given to you as well. And then once you have your F distribution, you'll be given your p-value, and then you can decide to reject or fail to reject the null hypothesis, and then state a real-world conclusion. So we're going on to our second to last review question. So just find the numerator and denominator for the degrees of freedom for the F distribution. This should be a pretty quick question. All right, great. So 2 and 242 are our numerator denominator degrees of freedom. If you remember, the numerator was between and the denominator was within. So you see the chart is just 2 and 242. So good job. So this is our last review. If our numerator degrees of freedom for the F distribution is 4, then what is K? Yes, good job, guys. So our k is equal to 5 because the degrees of freedom numerator is calculated by k minus 1, and then if we're given 4 as our numerator, k must equal 5 then. So good job, and that is it. Thank you guys for all coming. Good luck on your exam. I'll be sticking around for a couple minutes, so if you have any questions,